When precision toolmaker Heinrich Weber's grinding machine produced a surface finish measuring 2 microinches in 1914, inspectors thought their instruments were broken. But what if they had just witnessed the birth of precision manufacturing? September 14th, 1914, Cincinnati, Ohio. The gauge needle trembled at a reading that should have been impossible with existing grinding technology, and the 3 inspectors from Wright Engine Company stared at Heinrich Weber's test piece like it had materialized from another century entirely. Weber held the steel gauge block under the inspection lamp, watching light play across its surface with almost mirror-like clarity. The Wright inspectors had brought their own instruments specifically because they didn't trust the readings from Weber's shop. Chief Inspector Donald Mercer ran his fingernail across the ground surface, expecting to feel the microscopic ridges that every grinding operation inevitably produced. Nothing. If you want to see more videos about old machines, make sure to subscribe so you never miss another video. The surface was so smooth that Mercer's trained touch, calibrated by 15 years of inspecting precision parts, detected no discernible texture whatsoever. He reached for his Talisurf profilometer, the most sensitive surface measurement device available in 1914. The instrument used a diamond stylus to trace surface irregularities, recording deviations in millionths of an inch. Mercer made 3 separate measurements across different sections of the gauge block. Each reading came back between 1.8 and 2.3 microinches raw. For context, the best grinding machines in American factories typically produced finishes between 32 and 64 microinches. Even hand-lapped surfaces by master toolmakers rarely achieved better than 8 microinches. Weber's grinding machine had produced a finish 16 times smoother than what expert craftsmen could achieve through hours of manual work. "Your calibration is off," Mercer said flatly, though his voice carried uncertainty. "These readings would require grinding wheel surface, speeds and mounting rigidity that don't exist in practical machinery." Weber had expected this reaction. For 8 months, he'd been grinding test pieces that measured between 2 and 4 microinches, and for 8 months, every engineer who saw the results assumed measurement error rather than actual achievement. The problem was that ultra-smooth surfaces weren't just aesthetically pleasing, they were functionally critical for the emerging generation of high-speed machinery. Aircraft engines, precision bearings, hydraulic valves, and optical equipment all demanded surface finishes far superior to what conventional grinding could deliver. The gap between manufacturing capability and engineering requirements had grown into a chasm that threatened to limit mechanical advancement across multiple industries. "Test it yourself," Weber said, gesturing toward his grinding machine. "Bring your own steel stock, use your own inspection equipment, operate the machine under whatever conditions you specify. If my grinder can't produce these finishes consistently, I'll dismantle it and admit failure publicly." Mercer studied Weber's face for signs of bluffing or desperation. He found neither. What he saw instead was the quiet confidence of an engineer who had solved a problem that everyone else had declared fundamentally unsolvable. But could traditional grinding technology really achieve what only hand-lapping masters had previously accomplished? The morning shift bell at Turner Precision Works rang at 6:00 a.m. on a February morning in 1912, and Heinrich Weber walked past 15 grinding stations where skilled operators fought against the inherent limitations of their equipment. Each grinder produced the characteristic whining sound of abrasive wheels removing metal at thousands of surface feet per minute. But the resulting surface quality remained disappointingly inconsistent. Weber stopped at Station 7, where operator Frank Kowalski was finishing a batch of bearing races for electric motor applications. Kowalski had 23 years of grinding experience, yet even his expertise couldn't overcome the fundamental problems with conventional grinding technology. The bearing races required a surface finish of 16 microinches or better. Kowalski's grinding machine, despite careful setup and operation, was producing finishes ranging from 28 to 45 microinches. "Temperature variations in the grinding wheel," Kowalski explained when Weber asked about the inconsistency. "The wheel heats up during operation, expands microscopically, and changes the cutting characteristics. By the time I've ground 20 pieces, the wheel is cutting differently than when I started." This wasn't operator error, it was physics. Grinding wheels typically operated at surface speeds between 5,000 and 6,500 feet per minute. The friction generated tremendous heat that caused the abrasive wheel to expand, changing its effective diameter and cutting geometry throughout the production run. Weber had documented the extent of this problem across Turner's entire grinding department. Their monthly rejection rate for precision ground parts averaged 41%, representing $7,300 in wasted material and labor. More troubling was the reality that many parts that passed inspection were only marginally within tolerance. These marginal parts would fail prematurely in service, generating warranty claims and damaged reputation. The economic mathematics were stark. American precision manufacturing demanded approximately 89,000 ground components daily across industries from automotive to textile machinery. Each component required multiple grinding operations, with skilled operators earning $4.80 per day. The industry employed roughly 12,000 grinding specialists, yet surface finish quality remained the persistent bottleneck that limited mechanical advancement. Shop Superintendent Thomas Brennan stood watching Kowalski's work with the resigned expression of someone managing an unsolvable problem. "We've tried everything," Brennan told Weber. "Softer grinding wheels that cut cooler but wear faster. Harder wheels that maintain geometry but generate more heat. Different coolant formulations, variable wheel speeds. None of it produces the consistent finishes that modern machinery requires." What made the problem particularly frustrating was that hand lapping could achieve the required surface quality. Master lapping specialists like Edward Chen, who worked in Turner's tool room, could produce finishes measuring 4 to 6 microinches through patient manual work with progressively finer abrasive compounds. But Chen required 4 hours to lap a single bearing race to specification. Production demands required 40 bearing races per shift. The economics made hand lapping commercially impossible for anything except prototype tooling and the gauge blocks. The technical delegation from Zurich arrived at Turner Precision Works in May 1912, representing Switzerland's most prestigious grinding machine manufacturer. Their leader, Dr. Ernst Kellerman, carried credentials that made American engineers defer to his expertise automatically. Kellerman had written the definitive textbook on precision grinding theory, and his company's machines equipped the finest European tool rooms. Weber had arranged this visit specifically to present his early grinding experiments to someone whose opinion could influence American manufacturing. Kellerman spent 2 days examining Turner's grinding operations, measuring surface finishes, and reviewing production data. His conclusions were delivered with the certainty of established scientific principle. "The fundamental limitation is material physics, not machine design," Kellerman explained to Turner's engineering staff. "Grinding wheels are composed of thousands of individual abrasive particles held together by bonding material. Each particle acts as a miniature cutting tool, removing metal through fracture rather than controlled shearing. This process inevitably produces surface irregularities measuring 15 to 20 microinches at minimum." Weber raised his hand politely. "Dr. Kellerman, what if we could control the grinding wheel's cutting action more precisely, perhaps through wheel balance, mounting rigidity, or speed regulation?" Kellerman smiled with the patience reserved for promising students who haven't yet grasped fundamental concepts. "Mr. Weber, your optimism is admirable but misplaced. Consider mathematics. A grinding wheel operating at 6,000 surface feet per minute experiences centrifugal forces that create microscopic runout in even the most precisely mounted wheels. This runout, typically 0.003 to 0.008 inches, directly translates to surface finish irregularities." The Swiss expert pulled out a chart showing grinding wheel behavior under various operating conditions. Furthermore, the grinding wheel itself wears during operation. Individual abrasive particles fracture and are pulled from the bonding material, constantly changing the wheel's cutting geometry. Achieving consistent finishes below 10 microinches would require a grinding wheel that maintains perfect balance and geometry while simultaneously wearing a physical contradiction. Kellerman's American tour included presentations at 6 manufacturing centers, where he consistently delivered the same message. Ultra-smooth grinding finishes were theoretically impossible with rotating abrasive wheels. The only path to surfaces smoother than 10 microinches was traditional hand lapping by skilled craftsmen. Any engineer claiming otherwise was either delusional or fraudulent. These pronouncements carried enormous weight in American manufacturing circles. Machine tool buyers relied on European expertise when making capital investment decisions. If Dr. Kellerman declared that precision grinding below 10 microinches was impossible, then factory managers would continue depending on hand lapping for critical components, accepting the slow production rates and high costs as unavoidable. Weber attended Kellerman's presentation in Cleveland, taking extensive notes. The Swiss expert's certainty about grinding limitations wasn't arrogance. It was based on decades of practical experience and sound theoretical understanding. Every point Kellerman made was technically correct, yet Weber was convinced that Kellerman was solving the wrong equation. The question wasn't whether conventional grinding wheels could achieve ultra-smooth finishes. The question was whether grinding wheels needed to be conventional at all. The catastrophic wheel disintegration happened at 2:47 p.m. on August 3, 1912, and the sound of shattering abrasive material brought every machinist in Weber's experimental shop running to see what had exploded. Fragments of the experimental grinding wheel lay scattered across the safety enclosure, representing 3 months of development work and $890 in specialized materials now reduced to expensive debris. Weber stood staring at the destroyed wheel mount, his leather apron covered with fine abrasive dust. The wheel had been his boldest experiment yet. A custom-formulated abrasive using silicon carbide particles suspended in a revolutionary elastic bonding material that he'd hypothesized would allow the wheel to maintain geometry while cutting. Instead, the elastic bond had failed catastrophically under the centrifugal forces of high-speed rotation, throwing abrasive particles outward like shrapnel. His assistant, Paul Schneider, carefully swept up the wheel fragments while Weber documented the failure in his engineering notebook. The mathematical calculations had seemed sound. Reduce the grinding wheel's hardness to allow individual abrasive particles more freedom to self-sharpen while maintaining cutting geometry through elastic rather than rigid bonding. The theory was elegant. The reality was explosive failure that could have injured someone seriously if proper safety enclosures hadn't been installed. The Cincinnati Machinist Journal ran a brief article the following week. Local engineer's experimental grinder fails spectacularly. Experts vindicated. The article quoted 2 unnamed industry sources suggesting that Weber should abandon impractical experiments and accept grinding's well-understood limitations. But Weber's engineering notebooks told a different story for anyone willing to read carefully. He had documented 43 experimental grinding wheels over 18 months, each testing specific variables: abrasive particle size, bonding material composition, wheel density, and operating speeds. The elastic bond wheel wasn't just a random failure. It was a systematic test of whether flexibility could solve the geometry maintenance problem. 3 weeks after the catastrophic failure, Weber was examining the test pieces that had been ground before the wheel disintegrated. The first 20 parts showed surface finishes averaging 8.5 microinches, significantly smoother than conventional grinding produced. The surfaces weren't quite as smooth as hand-lapping achieved, but they were remarkably consistent, with finish variations of less than 1.2 microinches across the entire batch. Weber realized his elastic bond concept had been partially correct. The grinding wheel needed compliance to maintain optimal cutting geometry, but not elastic deformation under centrifugal force. What he needed was a wheel that was rigid during high-speed rotation, but compliant at the microscopic scale where individual abrasive particles contacted the workpiece. The solution wasn't in the bonding material at all. It was in something far more fundamental that every grinding expert had overlooked because it seemed too obvious to question. The wheel itself needed to be different not just in composition, but in fundamental operating principle. The revelation came at 11:30 p.m. on September 19, 1912, when Weber was examining a worn conventional grinding wheel under his newly acquired metallurgical microscope. The magnified surface revealed something that contradicted everything Kellerman had taught. The individual abrasive particles weren't cutting randomly. They were organized into microscopic cutting patterns determined by the wheel's rotation and the workpiece's feed rate. Weber spent the next 6 hours making detailed observations and calculations. Traditional grinding wheels operated at 6,000 surface feet per minute because conventional wisdom held that higher speeds generated excessive heat. But Weber's microscopic analysis revealed that the heat problem wasn't caused by speed. It was caused by each abrasive particle striking the workpiece multiple times as the wheel rotated, with each impact generating friction rather than efficient cutting. The breakthrough was counterintuitive. What if he increased the wheel speed dramatically while simultaneously reducing its diameters and changing its composition? A smaller wheel rotating much faster would bring fresh abrasive particles into contact with the workpiece more frequently, allowing each particle to cut once efficiently rather than striking repeatedly and generating wasteful friction heat. Weber's new design used a grinding wheel only 3 inches in diameter, 1/3 the size of conventional 9-inch wheels, but rotating at 18,000 surface feet per minute, 3 times faster than standard practice. The wheel composition was also revolutionary. Ultra-fine aluminum oxide abrasive particles, 400 grit compared to the conventional 60 to 120 grit, bonded in a vitrified ceramic matrix that provided rigidity without the thermal expansion problems of resin bonds. The mechanical engineering challenges were substantial. Rotating a grinding wheel at 18,000 surface feet per minute required a precision spindle running at 20,900 RPM. Conventional grinding machine spindles used ball bearings that would fail within hours at such speeds. Weber designed a hydrostatic bearing system where the grinding wheel spindle literally floated on a pressurized film of oil, eliminating metal-to-metal contact entirely. The bearing system maintained spindle runout below 0.0008 inches, 10 times more precise than conventional bearings. The workpiece mounting system was equally critical. Weber replaced the standard magnetic chuck with a custom-designed vacuum fixture that held parts with uniform pressure across their entire surface. This eliminated the microscopic distortions that magnetic holding forces created, distortions that conventional wisdom had accepted as unavoidable. Temperature control became the final crucial element. Weber's design incorporated a flood coolant system that delivered precisely temperature-regulated cutting fluid at 60 AgDAs directly to the grinding contact point at 12 gallons per minute, 4 times the flow rate of conventional systems. The coolant not only prevented thermal damage, but actually helped maintain dimensional stability by keeping both the grinding wheel and workpiece at constant temperature throughout the operation. On November 3, 1912, Weber's prototype grinder produced its first test piece. The surface finish measured 3.2 microinches. The skepticism Weber faced when demonstrating his grinder in early 1913 was immediate and absolute. When he presented surface finish measurements to potential customers, their first assumption was always that his instruments were miscalibrated. Theodore Morrison, production manager at Cleveland Bearing Company, expressed the prevailing sentiment directly. "Your measurements are either fraudulent or your gauge is defective. Nobody achieves 3 micro-inch finishes with a grinding machine." Weber developed a demonstration protocol specifically designed to eliminate doubt. He invited prospects to bring their own steel stock, their own measuring instruments, and their own operators to run his machine. He would grind test pieces under direct observation, then allow the prospect to measure the results with their own equipment in their own inspection rooms. Cleveland Bearing Company became his first test case in February 1913. Morrison arrived with 2 master toolmakers, a box of precision gauge blocks, and a Zeiss profilometer borrowed from their quality control laboratory. Weber's operator, trained specifically on the high-speed grinding protocol, ground 5 test pieces, while Morrison's team watched every step of the process. The first test piece measured 2.8 microinches on Morrison's profilometer. The second measured 3.1 microinches. The third, fourth, and fifth pieces all measured between 2 and 3.3 microinches. Morrison ran the measurements 3 times, convinced his instrument was malfunctioning. When the readings remained consistent, he asked to grind 25 additional test pieces to check for degradation over an extended production run. Weber's grinder produced all 25 pieces, with surface finishes between 2.4 and 3.7 microinches. The consistency was unprecedented in Morrison's experience. Even more impressive was that the grinding operation required only 40 seconds per piece compared to the 4 hours that hand lapping demanded for equivalent surface quality. The economic mathematics were transformative. Weber's grinder could produce in one 8-hour shift what would require 720 hours of hand lapping labor. Morrison placed an order for 2 grinders that afternoon, with a contract clause requiring that Weber personally supervise their installation and train Cleveland Bearings operators. The machines arrived in April 1913, and within 6 weeks, Cleveland Bearing had eliminated their hand-lapping department entirely. Surface finishes that had previously been bottlenecks achievable only through patient craft work were now routine production operations. Word spread through manufacturing networks faster than any advertising campaign could have managed. By autumn 1913, Weber had orders for 17 grinders. Factory managers who had initially dismissed his claims were now calculating how quickly precision grinding could replace their expensive lapping operations. The economic advantages were undeniable. Weber's grinder cost $3,400 initially, but eliminated labor expenses that totaled $780 monthly in typical applications. But Weber's growing success attracted attention he hadn't anticipated. Dr. Kellerman had learned about the American engineer whose grinding machines apparently violated fundamental manufacturing principles, and the Swiss expert was preparing a public technical challenge that would either validate or destroy Weber's reputation permanently. The public demonstration was scheduled for March 18, 1914, at the Cincinnati Industrial Exhibition, and Dr. Kellerman had designed the test protocols specifically to expose what he believed was either measurement, fraud, or unsustainable grinding practices. The conditions were harsh. Weber's grinder would operate continuously for 6 hours, grinding 180 test pieces from various steel alloys, while Kellerman's team monitored every parameter with Swiss-made precision instruments. The exhibition hall filled with 340 manufacturing engineers, machine tool dealers, and technical journalists. Kellerman had announced his intention to prove definitively that sustained precision grinding below 5 microinches was impossible with rotating abrasive wheels. His reputation guaranteed substantial attendance from engineers eager to witness either vindication of established grinding theory or the emergence of revolutionary manufacturing technology. Weber's operator began grinding at 9:00 a.m., with Kellerman standing directly beside the machine, observing the grinding wheel operation through a magnifying glass while his assistants monitored spindle temperature, coolant flow rate, wheel wear, and surface finish measurements on every 10th test piece. The first hour proceeded smoothly, with measured finishes ranging from 2.1 to 3.4 microinches. But at 10:47 a.m., the test revealed exactly what Kellerman had predicted. The grinding wheel was wearing. Microscopic measurements showed the wheel diameter had decreased by 0.023 inches over the first 90 minutes of operation. According to grinding theory, this wear should have produced progressively degrading surface finishes as the wheel's cutting geometry changed. Kellerman announced this finding triumphantly, suggesting that Weber's early success was temporary and unsustainable. Weber calmly explained that wheel wear was expected and compensated for through his machine's automatic wheel dressing system. Every 12 minutes, a diamond dressing tool precisely reshaped the grinding wheel, removing worn abrasive particles and exposing fresh cutting surfaces. This automated dressing cycle maintained the wheel's optimal geometry throughout continuous operation. The concept wasn't new. Wheel dressing was standard practice in grinding operations. What was revolutionary was performing it automatically with sufficient precision to maintain sub-4 microinch finishes. As the 6-hour test continued, Kellerman's skepticism gradually transformed into fascination. The surface finish measurements remained remarkably consistent, 2.3 to 3.6 microinches across 180 test pieces, representing 7 different steel alloys. The grinding wheel, despite continuous wear and dressing cycles, maintained its cutting performance precisely. Spindle temperatures stabilized at 73 degrees, just 5 degrees above the regulated coolant temperature. At 3:00 p.m., Kellerman made a brief statement to the assembled engineers. The results are verified. Mr. Weber has achieved what I believe theoretically impossible. The Swiss expert's endorsement eliminated any remaining skepticism about precision grinding technology. Within months, orders for Weber grinders were coming from manufacturing centers across America and Europe. By 1920, Weber's grinding principles had become the foundation for precision manufacturing in industries from aerospace to medical instruments, with many of his original machines still producing mirror finishes through the 1970s, proving that sometimes the impossible just requires someone willing to question what everyone knows must be true. But here's what nobody expected. Why did it take modern CNC grinders until the 1990s to consistently match the surface finishes that Weber's 1914 mechanical design achieved with nothing but precision engineering and fundamental physics?